All right, students, so now we're looking for examples of functions that are self-inverses. So let's start by finding the inverses of these functions. So with our first one, we've got x is 4 minus 2y. So rearranging this, y is going to be 4 minus x over 2. This is a function, so I can call it f inverse of x, but it's not a self-inverse because f of x does not equal f inverse of x. So not a self-inverse. All right, x equals 1 over y, therefore y is 1 over x. That is a function, so I can call it such, and f of x equals f inverse of x, therefore this is a self-inverse. All right, x equals y plus 1 over y minus 1. In this situation, I have got two different y's. I want to get them together somehow. So I'm going to multiply this to the other side. Xy minus x is y plus 1. I'm going to isolate my y's, so I'm going to pull them both to the same side. I'm going to get rid of this x. Now I'm going to factor out the y, and then isolate y. So that is a function, and it's the same as f of x, so this is a self-inverse. Remember earlier we also showed that 4 minus x was also a self-inverse. So let's graph all of these and see what happens to look for the symmetry of a self-inverse. So let's add in our functions. So we've got y equals 1 over x, and we've got y equals x plus 1 over x minus 1, and we also had y equals 4 minus x. So for all of these things, I want to think about what kind of symmetry they have, and it looks to me that they're symmetric across the line y equals x, because I could take any of these functions and sort of fold them in half. So remember, we said that a inverse is a reflection across the line y equals x. So any function that automatically reflects across the line y equals x must also be a self-inverse. So coming back here, we've got it's symmetric across the line y equals x.